So this lecture will just be a little bit of a review on statistical concepts. We will not be doing any math, so you can relax on that. I did present you a video under the week's work for class on the difference between inferential and descriptive statistics. It's like 3 minutes long. Please watch it. It's awesome on really breaking that down into a nutshell as to why these are important and different. You literally could have some descriptive statistics on your demographics even in a qualitative study, but inferential is more about making inferences about the testing that you did. We might also do some hypothesis testing, and so we'll talk about all of those things in this short little lecture. Basically, why in the heck do we want to do this in the first place? We need to look at different statistical testing, either I almost said demographics, but either descriptive types of testing or inferential statistics, in order to really look at our data. It is the highest level of measurement. It's going to give us something we can actually put our minds around and grasp. And as many of you already know, a lot of times if we're looking for statistical significance, we are looking for that less than 0.005. P is less than 0.005 for statistical significance, and that means something if you're looking in the evidence-based practice literature. So you're going to be more respected with your levels of evidence with statistical testing. Again, the video that I gave you really does describe this very well, but descriptive statistics are some of the things that we've really already talked about with measures of central tendency, but with descriptive statistics, we are describing what we already know. You know, this is the information that we have collected and gathered, and we're basically putting it in tables. We're giving some means. We might be talking about standard deviations. Of course, with univariate and bivariate, that is literally what it sounds like. Uni being one variable and bivariate being two variables. And I'll break down some more specific descriptive statistical tests in this lecture, but that's what it is in a nutshell. Whereas with inferential statistics, there are a lot of different inferential statistics types of testing, and that's what you have in your plans. But you might even want to go further and say, we will collect these types of descriptive statistics, and we will collect these types of inferential statistics, and we will do this type of hypothesis testing, just because now you will know. But with inferential statistics, we're trying to draw some conclusions about the population from our sample, whereas descriptive statistics, we are simply describing our sample population. We will simply discuss some of the different univariate descriptive statistical types of measurements. So some of the univariate descriptive statistics are where we are really looking at one variable on our population. It's basically just how we are displaying this data. You might have a list of raw data that you have collected. You might have, and that might really be from your demographic. You can do a frequency distribution. Maybe you guys remember what a frequency distribution is. I will show you that in this lecture. A frequency polygon is just another way to display the information, as is a histogram. These are all ways of displaying information that you know because you collected it, and it helps give a really good snapshot or picture of your sample population. Here is an example of univariate statistics for descriptive statistics, where it's just raw data, grades for a final exam. And so even I wouldn't use this because it's not really meaningful, it's not organized. Now, if I wanted to, I could look through, I could add all of these up and divide it by the number of exams that I have to get my mean. I could look for the mode through here. If you remember that, we can look to see what is the most common reoccurring number, and I believe it's 88. Looks like it's 88. I sat there and count these, but remember, mode is just not that helpful. But we could absolutely collect all of the information from central tendency from this list of raw data. This particular univariate statistic is a frequency distribution, and you can get this in SPSS or any type of statistical database. You can make your own. I'm sure if you've had statistics, and I know you have, you might remember doing this. And so basically what this does is it gives us the actual frequency. We also have some percents in this particular table, but it gives us the frequency or the number of times that a particular variable can occur in our population. And that's what it is in a nutshell. It is more useful than the raw data. You may also see in univariate descriptive statistics a frequency polygon, especially in articles, because it shows the shape of the distribution of our population. Histograms tend to be more popular, but this is really serving the same purpose as a histogram. It just shows it in a different format. And so this might be something that you would see in a research article to display the shape of the distribution of the population. This is an example of a frequency histogram. We get our mean, our standard deviation, our population, and it gives us the bell curve on there and gives us frequencies. This is probably the most common way that you're going to see data displayed in an article or even in a research poster once data is collected. Obviously, you guys don't have your data collected yet, but if you did, you might be able to use this. When you're counting up scores in this way, you're dealing with what we call frequency counts. We're counting the frequency of scores within a particular range, and rather than verbally describing the frequency counts, we present it in the form of a graph. And this graph is called a frequency histogram. And at its very basic level, it's a graph of each score within a sample. And this can also be generated really easy with any statistical program. So basically, everything I've talked to you so far is describing distributions. So let me give you a little bit to think about here. If we are talking about populations, imagine a population of numbers. Numbers between 1 and 10, and each number appears in a population with equal frequency. Each number appears maybe 4 times. If we randomly selected numbers from this particular population, each number would have an equal chance of being selected. So in the real world, actually the populations of numbers, or the scores on each variable that we are interested in, do not always appear with equal frequency. If we think about the number of teeth that you have filled as a dentist, according to an adult dental health survey from 1998, the mean number of fillings that an adult has is 7. So the proportions of adults with filled teeth in this particular survey is 7. Let us assume that this particular distribution of fillings is representative of all the adults in the UK, which would be about 3,800 adults in the survey, so that would be pretty representative. You can see or understand from that this large proportion of adults has between 6 and 11 filled teeth, and the vast majority have between 1 and 11. So we have a much lower proportion with no filled teeth, or with 12 or more filled teeth. And if you want to, the survey that I'm looking at is Kelly et al. 2000, and it's the UK Adult Dental Health Survey. So it's also in Pine et al. From 2001. So it's been looked at a couple times. You don't have to, but if you're confused by what I'm talking about. So the majority have between 1 and 11 filled teeth. That's what I'm getting at here. So we have a much lower proportion with no filled teeth or with 12 or more filled teeth. So you can see from this that if we randomly selected individuals from this population, that we're much more likely to select someone between 6 and 11 fillings than someone with more than 12. Hopefully that makes sense. So we randomly select from such populations. That way we don't have an equal opportunity of selecting each value on the variable of interest. So a distribution of numbers of fillings in the population could be made from this, and the shape of the distribution of scores is typically of many variables that we might actually be interested in health sciences, or for you guys nursing in health sciences. Statisticians have a name for this sort of distribution. This distribution is called a normal distribution. And I'm going to show you pictures of what each of these look like, but a normal distribution looks like a normal bell curve. It's bell-shaped, it's symmetrical at the peak, which is in the middle, and it tails off equally at both sides. We will also talk about when it tails to the right, which is a positive skew, or if it tails to the left and it's a negative skew, then it would not be normally distributed. There's also modes. And what that might look like is unimodal would obviously be 1, bimodal 2. Sometimes you come across distributions of data where there are 2 clearly identifiable peaks in the graph. And so that's a bimodal distribution, as the name suggests. And with multimodal, it would have multiple peaks. And so basically, that is what distribution of univariate data is it's the shape of the frequency or of the distribution of your population. Hopefully all of that sounded like a review of statistics, but I think that the pictures speak a lot louder than words. This is a normal distribution. As you can see, there is a nice bell curve. You can see that the mean is based on weight on the x-axis, and the mean is 150 pounds here. I will talk about standard deviations and how you determine things based on the skewedness in later slides, but this is a picture of a nice bell curve, a normal distribution. This shows a unimodal distribution, which is also a normal distribution on the left, and it shows a bimodal distribution. You can obviously see 2 peaks in the scores on the right. I couldn't find a picture of a multimodal, but it would have more than 2. Again, you do not have to do math for me, but just as a reminder, the standard normal distribution was your z-score, and it was z equals score minus the mean over the standard deviation. And so we have a symmetric, unimodal, normal distribution on the left here. In the middle, you can see that it tails to the right, and so that is positively skewed. And on the on the very right, we have a negatively skewed histogram that tails to the left. In order to understand any of these types of statistics, we have to talk about central tendency. And the mean, which I think you are most familiar with and you are going to see it most commonly, is the average. You add up all the values and you divide it by the number of values. The median is the point in a distribution where 50% of the scores are above it and 50% are below it. And then the mode is simply the number that if we look in raw data, like where I showed you the raw data, and we look for the number that occurs most frequently, we will get the mode. The mode is the least used out of all of the central tendency descriptors. In case you needed a review on this, I gave you some numbers. I added them all up, and we divide it by 11 because there's 11 of them, and we get a mean of 3.82. In order to get the median, we have all of these outlined out, and the median is 4 because it is right in the middle of all of these numbers, and it's 50%. Those are the numbers that are 50% below and the numbers that are 50% above. And the mode is the one that occurs most frequently, and so that should be 5. In creating a frequency distribution from the original raw data that I gave you on the test scores, we have a mean of 87.23 and a standard deviation of 7.04, and there were 43 test scores. And so in looking at this, it does not really appear to be a normal or unimodal distribution. It looks like we might have a bit of a bimodal, and it is certainly not symmetric. It is positively skewed to the right, which is normally what I see in your test scores as well. One of the other things that we want to look at are the measurements of variability. And so a range is the highest score minus the lowest score. And so if we're looking at this example, 8 is our highest score, 0 is our lowest score, so the range is 8. And then if we look at the test, we had ranges from 70 to 98, so 98 minus 70 would be 28. And then standard deviation is the average amount the scores vary from the mean, and we get this by doing the z-scores. There's probably a better example of this in your textbook, but really what I wanted to point out, this shows A and B to show you differences in standard deviations, but there is a formula. It's 68, 95, and 99.7, and so I'm not asking you to memorize all of that, but when I do get those questions on statistics, or if I'm looking at a research article and I'm trying to determine this, I draw this little bell curve and draw my numbers on the x-axis. And so, for example, if you will look down here on the x-axis, you see numbers between 100 and 200, and that's supposed to represent weight in pounds. So the mean is 150. So if I had scores between 140 and 160, then that would represent a 68% probability of selecting a score within this region. Now, if I went out a little bit further and I went to, 125 to 175, then I would have a 95% probability of selecting scores in that range. And then if I went out even further and went out to, say, the 105 to 195 area, then I'd have that 99.7% probability of selecting scores within that range. So this is basically just showing you test scores again as an example, and these are two frequency distributions. On the left, we've got 28 scores, a mean of 79.4, and a standard deviation of 10.25 between the scores. It looks more bimodal to me. It is still a normal distribution. This one is completely normal. It doesn't look skewed in any way. It's a nice bell curve. 60 was the lowest score, 100 was the highest score, and as you can see, the averages really are between that 75 to 85, about 68% of the scores are within that range. And then between 70 to 90, the 95% of the scores are between that range, and then that 65 to 95, the 99.7% of the scores are between that range. And then on the right, we're slightly skewed to the right on this one. Scores range between 65 to 100. There were 36 tests. 84.9 was the average or the mean, and there's only 7.39 standard deviations between the scores. And it looks more unimodal, and as you can see, 68% of the scores are between 80 and 90, 95% of the scores are between 75 and 95, and then the 99.7 would be between that 70 to 99. Now, These are
So
some
that
things that you
is a
need
nice,
to know about standard
slightly
deviations.
skewed
You
to the
need
right
to know this information.
frequency
Hint, hint,
distribution.
hint. The smaller the standard deviation is, the more homogeneous the scores are. Okay, so in that last one that we just looked at with the 7 point whatever, the standard deviation, you can see that the scores were pretty similar there, and that's why it was a little skewed to the right. There's less variation in the scores around the mean. The better the mean is as a summary of a typical score. And the more narrow the shape of the distribution is. It should probably be more unimodal. Now, on the flip side, the larger the standard distribution is, the more heterogeneous are the scores. There's more variation in the scores around the mean. The worse the mean is as a summary of a typical score, and the wider the shape of the distribution. This is just a summary of what I already said about that normal distribution. If you look at the X at 500, that would be your mean, and you can see that 400 is one standard deviation, 300 is two standard deviations, 200 is three standard deviations going to the left, and then 600, 700, 800 are the 1, 2, 3 standard deviations. Between 400 and 600, you would get 68% of the probability of those scores, and then between 300 and 700 would be the 95% probability, and then between 200 and 800 would be your 99.7 of those scores falling within 3 standard deviations. So literally, when I'm being asked these types of questions, I will make my little curve and draw this out, and it's really easy. This is simply another pictorial example of what we've discussed about the quartiles, and X is the mean, and looking at the percentage of those scores around the standard deviations and getting your probabilities. So here is an example. You've got SAT scores that are normally distributed, a mean of 500, that's in the middle, and a standard deviation of 100. And in a sample of 800 people who took the SAT, how many of them had scores between 400 and 600? I hope you got 68%. So on this one, you literally have to not use this example and write it all out like I did. So in a sample of 900 people, so you're going to have to make a bell curve and make 100 on the very left and 900 on the very right. And then your mean is, it's normally distributed, but your mean is 280, so that's going to be in the middle. And then, so from that, how many of them had scores between 160 and 400? And that really should mark, and your standard deviation is standard deviations of 60. So that really should mark us about 95% probability of getting scores in that area. And then if you do this between 160 and 400, excuse me, if you do it between 160 and 400, then you've got about 95% of them. And then if you go on to do this at the mean point, between 280 and 340, that's only at about the 68% mark. Now we will move into bivariate descriptive statistics, or measuring two variables. So, a bivariate relationship is where one variable shows an association or a correlation with a second variable. There are bivariate correlational techniques to assess the strength and magnitude of an association or a relationship, and the associated p-values shows us whether the relationship is likely to be due to a sampling error or chance. So there's correlational techniques that are not used to assess the differences between variables. We'll talk more about hypothesis testing later on in this lecture, but basically when we're looking for a relationship between two variables, we're trying to ask what extent, to what amount are the two variables related. And so if there's a positive relationship, as a value of 1 increases, the value of the other variable increases. So they are positively working together. Whereas in a negative relationship, if the value of 1 increases, the value of the other variable decreases. And if there's just no relationship at all detected between the variables, then there's no relationship. You can plot this type of data on what's called a scatter plot. Here's a really nice example of a perfect positive correlation. You can see scores A on the x-axis and scores B on the y-axis, and you can see as score A goes up, score B goes up. And so that is a perfect positive correlation. In thinking about relationships, what kind of a relationship might you expect between a patient's grip strength and their arm strength? I couldn't call it perfect, but it's absolutely a positive relationship between someone's grip strength and their arm strength. Here we've got measurements of between 20 and 200 on grip strength and 10 and 140 on arm strength, and you can certainly see that the data is moving diagonally towards the right, which is a positive scatter plot relationship. Keeping that in mind, then what kind of relationship would you expect to see between someone's self-esteem and their anxiety levels? A negative relationship. On this particular scatter plot, if you look at the x-axis, we can see the self-esteem scale, and on the y-axis we see the anxiety scale. So when we look at the number for the self-esteem and we look at the number of anxiety, we see that as anxiety increases, self-esteem decreases, and so that would be a negative relationship. And this one is more horizontally shifted to the left. Instead of using a scatter plot, you could actually calculate a correlation coefficient known as Pearson's R, and I notice that some of you are absolutely using this in your projects, which is great, because basically this is a parametric test to assess correlational relationships. It's called Pearson's product moment correlation, but we know it lovingly as Pearson's R for short. Parametric tests are used when your data is normally distributed. So you've got to have normally distributed data to use it. If your data is skewed, it's recommended to use non-parametric or Spearman's rho to calculate the relationship. So the strength of a correlational relationship is measured on a scale from 0, or no relationship, to +1, which is a perfect positive relationship, and from 0, or no relationship, to -1, a perfect negative relationship. The nearer to 1, whether it's negative or positive, the stronger the relationship is. The nearer to 0, the weaker the relationship is. If all data points fall on a straight line, then the relationship is said to be perfect, and Pearson's R would then be 1. It's pretty much impossible to find a perfect relationship when carrying out research, so you're going to be trying to determine if you have a positive or a negative relationship or no relationship at all. Pearson's R uses interval and ratio level types of variables, and it describes two things about the relationship: the direction and the strength. And so if the relationship is positive, as one variable increases, the other increases. So that's the same as we were talking about on the scatter plot. With a negative relationship, as one variable increases, the other decreases. The strength of the relationship is the number that I've already discussed with you. If it is 0 to 1, or if it's -1, it's probably a negative relationship on the strength, and if it's +1, then it is a positive relationship. The closer the number is to a -1 or a 1 as opposed to 0, the stronger the relationship. Even though you likely will not see this, this is considered a perfect positive correlation, with the score A being on the x-axis and score B being on the y-axis. Your Pearson's R, where R equals a +1, because as the scores go up on A, the scores go up on B, and they consistently lean to the right from that left hand 0 all the way up horizontally, all the way across the board diagonally. They are leaning to the right. Whereas with a negative relationship, you'll really mainly see it almost from the other corner, like at 12 going the other direction with a negative correlation. So this is a nice perfect positive correlation for Pearson's R. Guess I should have said that depending on how your data is set up, because score A is on the X and score C is on the Y, and because they are negative, the way that that's set up, it goes diagonally from 0 towards 12, but it's a Pearson's R of -1, and so this is a perfect negative correlation. Again, you're probably not going to be seeing these perfects ever. Very, very rarely are you going to be seeing perfects in research, but we're trying to get close to 1 to show strong relationships. If it's closer to 0, then we don't have a strong relationship either direction. What kind of relationship or correlation would you expect to see between a GPA and an SAT score? I wish we had this on an ACT score instead, because I haven't seen SATs very frequently anymore, but we actually still have this in the research, and if you can see on the x-axis, we have SAT scores from 400 to 1600, and we have GPA ranging from 1 to 4, and the relationship is 0.8, and it's a positive 0.8, so that is a really positive, strong correlation between GPA and SAT. As the scores go up, they both go up in the same direction. Conversely, yes, they've actually done this research. What is the correlation or relationship that you might expect to see between GPA and height? R equals 0. As you can see, it is all over the place. We have height on the x-axis, GPA on the y-axis, and there is absolutely no correlation, no relationship between someone's GPA and their height. Other interesting educational research that has been done: what kind of relationship would you expect to see between number of alcoholic drinks per day and GPA? Now granted, this particular study would be self-reported, but it is a negative relationship, and it's a strong one. It's -0.8, and that is because as someone had more drinks, their GPA dropped, which makes sense. But again, that's those that were admitting it. So it shows you that if you look at towards the 4 all the way down, it's going in that diagonal direction to the left. More drinks, less GPA. What I absolutely want you to understand is, if you were to look at being given Pearson's R, would a -8.4 or a +6.9 points, I should say 84%, -84%, or +69% have a stronger correlation? And the answer is that the -84% has a stronger negative correlation than a +69% correlation. They're both strong, pretty decent relationships, but the closer that you are to 1, the stronger the relationship, whether positive or negative. Also, you need to remember that correlation does not imply causation. So when we talked about a strong causation between skin cancer and time in the sun or sunburns, that's causation. correlation is measuring the strength and the direction of the relationships. They are different. Now, we have discussed descriptive statistics and how we would actually take what we've gathered and what we already know and display it, whether we're talking about univariate with one variable or bivariate with two variables. Now we're actually going to talk about inferential statistics, which is different because this is how we are actually implying some things about the data that we've gathered. Inferring. Remember, in any kind of research that we're doing, we aren't looking at the total population. We're looking at a sample of the population, and we want it to be transferable and generalizable to the entire population. That is our whole goal. So do the findings from our sample actually tell the truth about the entire population? So a statistic then is just an estimate of a parameter. Statistic over sample size equals parameter of the population. So I like to call these snapshots. Statistics estimate parameters. And parameters are really what you want to know to be able to make your data transferable and generalizable. With inferential statistics, they are based on the laws of probability. And so they assume some random selection took place and that the research question is answered using hypothesis testing. Remember way back when we talked about the hypothesis and the null hypothesis, and we'll review that a little bit. But that is what inferential statistics is all about. So, back to talking about hypothesis. Remember, HA is your research hypothesis. I always remember the A as the alternative, whereas HO is your null. But here's a research hypothesis example. Pregnant women who watch a video on breastfeeding will breastfeed their babies longer than pregnant women who do not watch the video. And so this is a research hypothesis that we want to test. The null hypothesis then would be pregnant women who watch a video on breastfeeding will not breastfeed their babies longer than women who watch the video. So the video makes no difference in the time of breastfeeding. That's your HO or your null hypothesis, no difference. Randomly select and assign to groups. If we do an experimental group here, that's going to be the group that we're manipulating with our intervention, and they're going to watch the video. Control group, they just do they do their traditional, they do their own thing, they're not going to watch the video. Then you get your results. The mean number of days that women in your experimental or interventional group breastfed was 131.5. The mean number of days that your control group breastfed was 125.1. So can the researcher claim that the video is effective in extending the length of breastfeeding? It did extend it, right? But by how much? There's only two possible answers. Was your null hypothesis not true, or was your because remember you have to work with your null hypothesis. So the video was effective in extending breastfeeding, or the video wasn't effective, and the results are due to chance. So the hypothesis, the null hypothesis is true, or the null hypothesis is not true. What do you think? Obviously, we would like to reject the null hypothesis. That is the whole point of doing the research in the first place. But you don't want to reject a true null hypothesis, because then your research is fabricated or there's an error that could have occurred. The two errors that the researcher could make is a type 1 error and a type 2 error. We have actually discussed this before, but just as a reminder, a type 1 error is what happens when the researcher rejects a null hypothesis that's actually true. A type 2 error occurs when you fail to reject a null hypothesis that's actually false. So you want to do whatever you can to minimize the risk of making either of these types of errors. So in order to make sure that we are setting some parameters here to limit our ability to make those errors, the researcher sets a degree of risk that they're willing to take to reject a true null hypothesis. So say you want to be right 95% of the time, that you're accepting the probability of being wrong 5% of the time, not 6, not 10, yada yada yada. You're saying that you want to be right 95% of the time, but you understand and you accept that you could be wrong 5% of the time. That means that you're willing to reject a true null hypothesis 5% of the time. If that's what you choose, then your level of significance, or your alpha, is p equals 0.05, a 5% probability of rejecting a true null hypothesis, which is what we are used to seeing, somewhere between that 80 and 95% significance level. 95 is kind of the standard. What you will see most typically in nursing research is that p equals 0.05. I'm okay with being wrong and rejecting a true null hypothesis 5% of the time, or the most common one that we'll see, especially in larger studies, is p equals 0.01. I'm okay with being wrong and rejecting a true null hypothesis only 1% of the time. So run the statistical test on your data, and remember, you're testing if the null hypothesis is true. We use a computer, we use SPSS to give us this results, and that's how we get our p-value, or our probability. And this is the probability of getting those results if the null is true. If you get a high probability, the p-value, that you get your results if the null is true, do you think that the null might be true? Yes, you can't reject it. If you get a low probability, the computer p-value, that you get your results if the null is true, it might be true. It's not. You would reject the null hypothesis if you get a low probability. So what you need to know out of this slide, and what you need to know for this, is that when you're doing this particular hypothesis testing, a high probability p, so say you get a p of, 5, then you can't reject your null hypothesis. But say you get a p of 0.0001, then you get to reject the null. And I'm just throwing out some numbers there, but it depends on what you set it at. You want to, make sure that your p is set at the that it's within the significance that you set. How do you make your decision? I just kind of went over that a little bit, but if your p-value that you get from the computer or from SPSS is less than or equal to the value that you set, you get to reject the null. Yay, it was significant. If the p-value from the computer is greater than the p-value you set, you fail to reject the null, and your result is statistically non-significant, which is disappointing to researchers, but it's still valuable research. And there are more examples of this in the study guide. Hint. Now, there's actually a difference between statistical and clinical significance. A result might be statistically significant when it's calculated p less than 0.05, but it's only clinically significant if these results can make a difference in people's lives. For example, a new drug study is statistically significant in lowering blood pressure, but if it only lowers systolic blood pressure by an average of 0.264 millimeters per mercury, so what? Really? I mean, how is that going to affect someone's life? If positioning shortens the length of second stage of labor by 36 minutes, is that clinically significant? I would say yes, and I would say that that would be statistically and clinically significant. Parametric statistical tests have a dependent variable that's measured on the interval ratio scale, as we discussed earlier. You need to have your data normally distributed. There needs to be random sampling in place because of all of these statistical rules, and your groups need to be mutually exclusive. If you couldn't follow all the rules because of how your test is set up and how your research had to be done based on your sample, that's okay. There's something called non-parametric testing. Makes no assumptions about the shape of the distribution. Ordinal and nominal scale data is used on this particular type of testing. It's a little less powerful than your parametric testing, but it still gives us data. Correlational types of data with parametric is Pearson's R. With non-parametric, we're talking about Spearman's rho. It measures a relationship between the two variables. The coefficient is -1 to 1. Remember, the closer you are to 1, whether it be negative or positive, the stronger the relationship. And you've got to consider the p-value and the correlation coefficient. With parametric procedure, we're talking about Pearson's R. The t-test is a great statistical test. I know it's one that I'm using in my research. I saw that a lot of you chose it as well, and it may be because it's the example I gave you and it's easy to go to, or it could be because there really aren't nearly as many rules with this one and we still get something good to look at and use for an inferential statistic. Because really all the t-test does is look at the means of the two groups and determine if they're significantly different. Like what we talked about earlier with these breastfeeding moms, we could get a really quick t-test on that and say, hey, are these statistically different than what I set up on for my parameter of my p is less than 0.5 or 0.05, excuse me. Both groups must have similar variances with respect to the dependent variable. That is certainly something that you have to look at. So if you're using the same groups to do a pre-test and a post-test, t-test is perfect for you. There are two different kinds of t-tests that might be used, t-tests. I always want to call them t-test, and that's not correct. You can do independent, which is comparing two independent groups and the variances are not equal, or you can do dependent t-test, which compares the scores between groups, a pre-test, post-test, correlated groups, matching subjects in two groups. So dependent t-test is used a lot of times more frequently, gives you a little bit more leeway. But if you're just doing two independent groups, two different groups, then you're doing independent t-test. If you are doing, similar groups, comparing their scores, you want to look at differences and similarities between those groups, or you're doing pre-test, post-test, or you're trying to make some type of correlation between them, or you're matching different subjects in the two groups, then you're talking about dependent t-tests. ANOVA is actually looking to find out if there is a significant difference about 3 or more different types of group means. The difference between a t-test and ANOVA is the number of groups being compared. There's a one-way ANOVA and then there's a two-way ANOVA. There's a within a group and between a group variance for the total variation, and you get an F statistic with ANOVA. I did want to go ahead and mention that with this analysis of variance, we're looking to find out whether there are significant differences between the conditions or the groups. There's another type of statistical test called ANCOVA. This is a little bit more advanced for sure, but we're not doing the math anyway. We'll get a statistician, right? So analysis of covariance is a statistical technique where differences between the conditions are analyzed after controlling for and pulling out specified variables. Those are the covariates. So that is another type of statistical test that you could look at doing. And then I don't have a slide on it, but I wanted to mention it because a couple of you discussed doing multiple regression. Again, this is an advanced technique, but it's a correlational technique that assesses the relationship between a set of explanatory or predictor values and a criterion variable. So this gives you a lot more information if you've got multiple variables going on. Another really common test people use is a non-parametric statistical test, so you don't have to have an evenly distributed population here or sample size, and that's chi-square. This compares the frequency of an observed occurrence with the frequency of an expected occurrence. And you can use nominal data on this one, so it can be a quasi-experimental study that you can use chi-square on. It compares counts, not means, and so if you've got a sample, their number of responses, the number of objects or subjects that fall into 2 or more categories can be evaluated, and this is an easy type of statistical test to complete, so this is one that we might see more commonly in research studies as well. An example would be like C-sections compared with the rate of standard birth. That's one sample. Is it a good fit or a bad fit? In summary, I understand that a lot of these statistical measurements and tests can be like the cell cycle. It was for me too. And I am by no means a statistician, and I am not an expert on it, but I hope that this gives you a guide and a little bit more information on the difference between descriptive and inferential, and what hypothesis testing means, and what type 1 and type 2 error means, and statistical versus clinical significance. All of those are really the main items to get at this, and hopefully it gives you another perspective on what type of analysis plan you would want to do for your own research.